Have you ever stopped and wondered how we measure things that seem, well, immeasurable? You know, like the total force of water pushing against a massive curved dam, or all the energy a city uses over a single day. You can't just pull out a ruler for that stuff. So how do we do it? Well, the answer comes from a really elegant and surprisingly simple mathematical idea. Let's dive in.
Okay, here's our game plan. We're going to start by understanding the basic problem, which is finding the area under a curve. Then, we'll look at how a simple shape you learned about in school gives us a clever solution. After that, we'll see how to crank up the accuracy of that solution. We'll even figure out how to know exactly how good our guess is, before, finally, seeing how this one rule helps build the very world around us.
So, it all starts with this idea called integration. And honestly, that's just a fancy math term for finding the area under a curve. Now, for shapes like squares or circles, that's easy, right? We've got formulas for those. But what about the weird, complex, kind of wobbly curves you see in real life? Yeah, our basic formulas just aren't going to cut it.
So that brings us to the big question. If our simple formulas don't work, what do we do? How do you possibly measure a shape that just doesn't play by the rules? Well, the answer is you have to get clever and find a way to approximate.
And here's where we make our first move. Instead of trying to deal with that complex curve all at once, we're going to use a shape we actually understand, a simple trapezoid. You can think of this as making a really rough, first-pass sketch of the area we're trying to figure out.
And this is the trapezoidal rule in a nutshell. It's what's called a numerical method, which just means it's a practical way to get a number for an answer, even if it's not a perfectly perfect one. All we do is pick a start point and an end point on our curve, and bam, draw a straight line between them. That line becomes the top of our trapezoid.
And the process itself? Super straightforward. First, you pick your start and end points. Second, you just connect those dots with a straight line. That line, the base on the x-axis and the two vertical sides, that's your trapezoid. And the area is easy to calculate. It's just the width of the base times the average height of those two sides. Simple.
But you can probably see the problem here, right? Look at that gap between the straight top of our trapezoid and the actual curve. That space, that's our error. It's a decent first guess for sure, but there's obviously room for improvement. The good news is, we can do so much better.
And this is where the whole method gets really powerful. I mean, if one big trapezoid is like a blurry, low-res sketch of the area, what do you think happens if we use a whole bunch of tiny little trapezoids instead? This is how we go from a rough sketch to a crystal clear, high-res image.
This lays out the trade-off perfectly. One trapezoid? Super simple calculation, but your error could be massive. Using a ton of little trapezoids? Yeah, it's more calculations, but your accuracy just skyrockets. You're basically filling in all the details, getting that high-resolution picture of the real area.
And this is the multiple segment trapezoidal rule. We just slice the area up into a bunch of smaller, equal-width segments and make a tiny little trapezoid for each one. And because those segments are so narrow, the straight tops of the trapezoids start to hug the real curve much, much more closely. That cuts our error way down. Then we just add up the areas of all those little guys to get our final, much better answer.
Okay, so we've got our high-res answer. But you know, in science and engineering, just getting an answer isn't quite enough. You have to know how much you can trust that answer. So, how good is our guess really? And is there a predictable way to make it even better?
And the answer is a huge yes. The most amazing part is that the improvement isn't random at all. It actually follows a very specific and incredibly useful pattern.
And there it is. This is the absolute golden rule of this method. Every single time you double the number of trapezoids, say going from 10 to 20 or from 50 to 100, you don't just cut the error in half. No way. You slash it down to a quarter of what it was before. This is an insanely powerful relationship. It means we can literally dial in whatever level of accuracy a problem needs.
See, this isn't just some neat math trick we do on a blackboard. This is a foundational tool of modern engineering. It helps us, quite literally, build our world. This method is what turns these complex, theoretical problems into practical, real-world numbers that let us design and build things that work.
And just think about how widely it's used. Chemical engineering, civil engineering, computer, electrical, industrial, mechanical. From figuring out chemical reactions to designing bridges, from creating computer chips to managing power grids, it's a fundamental tool that shows up everywhere.
Seriously, just picture it. An engineer trying to figure out the total force pushing against a huge curved dam, they're finding the area under a curve. Modeling the flow of electricity in a power grid over 24 hours, they're integrating a complex function.
the trapezoidal rule is what makes these kinds of crucial calculations actually possible.
So if you're going to take one thing away from all this, let it be this. The trapezoidal rule is just a beautiful way of solving a seemingly impossible problem through smart approximation. By chopping up a big, messy shape into tiny, simple pieces, we can measure just about anything, building a better and better answer, one segment at a time.
And that leaves us with one last little thought to chew on. The power of this whole thing came from using simple, straight lines. But what if we didn't have to use straight lines? What if we used a slightly more complex shape, like a little piece of a parabola to approximate each segment of the curve? Could we get an even more accurate answer? Maybe even faster? Something to think about.